Hello everyone. We are continuing on our chapter 2, section 4.2 on area. So last time we talked about rules of summation. So these rules are very important because today we will be continuing on finding the area of a plane of a region, and we'll be using these summation rules over there. And also, if you remember, we talked about how to find these, use the rules to evaluate this expression using the above rules. And then we looked at, then I would like you guys to work on some of these practice problems. So this is important, guys. These are practice problems based on what we did in part 1. So please work on them. So you have to write the sigma notation. In other words, what I'm looking is what is equal to sigma, and then I want you to write down what the values will be here, the lower end and the upper end, and then the expression. Similarly for each one of them. Just go ahead and do that. And then you will be applying to evaluate the sum using these same properties to evaluate the sum. In other words, write it in the expanded form. Like I'll start this one, so it's 9, how many times? 9 plus 9 plus 5 times 3, 4, 5, and you know what the answer would be. Similarly, go ahead and do all of them. So we know definitely the answer is, because it is what? It is 9 times 5, right? So you can write like this as 9 times 5 if you remember the rules of the summation. Or you can open it up and say it. So the answer would be 45. Similarly, go ahead and do the rest of the 3 problems. And now we would be looking at area of a plane region. So let's look at this one. Suppose we have a function. We have a function minus x squared plus 5. I like to find the area under this curve. So basically I want to find this area, which is under the curve and above the x-axis and bounded by vertical lines. This is your x equal to 0 and this is your x equals 2. Okay. So we like to know what is this area. Now in order to do that, if we go back to our various things which we did when we were in elementary school, our teacher would put this nice little curve on square sheet and say, okay, find the area, every square is 1 unit. So we're going to use that kind of an idea. So what we're going to do is we are going to actually inscribe and circumscribe some rectangles in this one. So area of a plane region, guys, you can see spelling is wrong, but that's okay. Okay, so what you're basically doing is this. This is a graph of quadratic function. We already see that. So what we're going to do is, okay, we're going to put some rectangles. And these rectangles are going to be below. So we call them area of the inscribed rectangles. So we really know it's a nice geometric figure. We can find the area of these rectangles. This rectangle is base into height. Similarly for this. So we can approximate the area under the curve by adding up all the area of these rectangles. Definitely we will know that this area under the curve is going to be more than this area inscribed by these rectangles. Or somebody would say, oh no, I would like to put the rectangles above the curve. Okay, so we can have these rectangles which are circumscribing the function we're having. So this way, when we find the area of these rectangles, guys, will have area more than the area under the curve. So that is the picture we are going to look at. Okay, so that's the bigger picture. Now suppose I would like to know, do we only have to have 5 rectangles? So what happens if I increase these number of rectangles? So let me just show you if I increase the number of rectangles. So instead of having, say, 1, 2, 3, 4, 5, suppose I'm increasing the rectangles. I have, say, at least 10, okay, or say I'm going 3 here. It's not a nicer one, but you get my point here. So I'm going to get, so every rectangle I'm increasing. So what is happening? Oops, guys. Okay, so you can see what I'm doing. Oh no. So my rectangles, the lines you can already see are kind of little crooked, but that's okay. Okay, so we'll try our best. So notice what is happening. If I'm increasing this, rectangles. So the area which when I add up all these rectangles is coming more closer to the area under the curve. So that's the idea we will be looking at. So, and that's where the lower and the upper sums come into play. So guys, I tried my level best. Oh, finally! This was the one little rectangle which has a nice little vertical line. Everybody else you could see a little off. But let's go to the main part of it. So the main part says that when we are increasing the area of the rectangles, okay, so we say we look at it in terms of the lower. So area of the inscribed rectangles, so that's what we had, the area of the inscribed rectangles, which is basically the width of the rectangle delta x times f of small mi. Now the small f of mi is the minimum value of that function in that interval. So let me give you an idea here. Suppose I have this curve and I have drawn a rectangle here which is inscribed. So notice in this one, the minimum area, the minimum length is given by this. Do you see this one? So in this whole region, if this is the width, the minimum value is given by this. On the other hand, so that's what we say. So the area of the rectangle is width times the height. So this is the minimum height which can inscribed in this with this width. Or if I'm looking at the highest, so if I go for circumscribed rectangle, when I go for circumscribed rectangle, say if I have this one, circumscribed is this. Okay, so here's the circumscribed rectangle. So the circumscribed rectangle, this one which I'm just squiggling like here, this guys is the maximum height in this rectangle. So that's what it says. So clearly the area of the inscribed rectangle we already know is less than the area of the circumscribed rectangles. So we gather all of these rectangles which are below the curve, we call them the lower sum. We represent this by S of sub n. And when we add up all the circumscribed rectangles, we call them the upper sum. And we're in this form, summation I run to n. Suppose there are n rectangles, f of capital Mi, delta xi. This one is the maximum value of the function in that interval. Okay, so let's look at it in terms of pictures which make much more clarity to us. So here's the circumscribed rectangle. So here's the area, is the function we are given. You want to find the area under the curve from A to B here. Suppose this is what we want to know, the area under the curve from A to B. Here's my A to B here. So this is what we find. So if we have inscribed rectangles, this area is definitely less than the area under the curve. But if we have circumscribed, that is more than. So what we notice is this is big because when you add up all the inscribed rectangles, we get a lower sum. So the lower sum is less than the area of the region, which is less than capital S of n, which is all the upper sums. Okay, so here's this. So if I increase these number of rectangles, that means if I take the limit, which is the next slide telling us, so if I take the limit of Sn as n tends to infinity, it is the limit as n tends to infinity of summation of f of mi. Remember, this is the minimum height in that ith interval, which is equal. So if you increase the number of rectangles and n tends to infinity, it becomes so close that these limits of the lower sums is the same as the limits of the upper sum. And this delta x, guys, to make our life simpler, we're going to take b minus a over n. And we're going to assume that we are having all the rectangles which are inscribed or circumscribed are of equal width to make our life simple. Okay, so let's do an example. It says find the limit of Sn. Now remember, what is my Sn? It is the lower sums. as n tends to infinity. In other words, it says, what is the limit as n tends to infinity of s of n? These are all the lower sums. You don't have to worry about, we just have to go and apply what we have learned. So limit as n tends to infinity, 1 over n squared, n into n plus 1 over 2. Now remember, we're going to go back to our chapter 1 and chapter 3 here. We're going to do the limits as well. At the same time, we are applying limits to infinity. Okay, just to remind you guys, so if we had limits to infinity, remember limits of n to infinity of k over n is what? Where k is a constant, is always 0. If you remember that, guys. Because if number becomes very, very large, 1 over a large number becomes very, very small. Remember that. Okay, so what are you going to do? So this is a constant. We can pull the constant out. If you remember from the chapter 1, the constant is not needed. So limit n tends to infinity. What do we have? N over n plus 1 over n squared. Now clearly one of the n's can cancel, right? This and this cancel out. So what are we left with? Have limit n tends to infinity n plus 1 over n. Now it's much more better to open this up. So it's limit half, definitely. Now you can separate the terms. It is n over n plus 1 over n. So what are we getting here? We're getting half limit n tends to infinity 1 plus 1 over n. So what happens when I apply the limit to this expression? This one goes to 0. Remember that? That's what we're doing. This goes to 0. What are we left with? Limit as n tends to infinity of 1, 1, 1, 1 is basically 1. So what do we get? Half times 1. Final answer, half. Okay. Now we are going to combine this limit with the summation rules we learned earlier. So that's the next example, guys, we're going to look at. Now it says find the formula for the sum of n terms, and we use this formula to find the limit as n tends to infinity. So before we can apply the limit, we have to open this, the summation rules, guys. That's what we're going to do over here. Okay. So the first thing we're going to do is, remember, the constant can be pulled out and n is not needed at this point. N has to be out because the I variable is on this expression. Everything else is like a constant for the summation. So let's write that down. So we have limit n tends to infinity. Now 2 and times 2 is 4. And we're going to take, this is a constant. Remember, what's this equal to? It's 4i n squared. Now 4 over n squared is not the one where my I is relating. My I is only concerned with this little part. This I, guys, is what we are going to do, is the one summation acts on. Everything else is a constant for it. So we take the 4 over n squared out, summation. Now this I is only on this. I varies from 1 to n of I. Now this is the sum of first n terms, if you remember. And you have to go back to the formula. Make sure, as I said, keep the handy formulas, okay? Limit 4 over n. What is this? Sum of the first terms is n into n plus 1 over 2. Oh, that's n squared. I forgot that. Sorry, guys. Okay. Now let's do some cancellations. So 2 and this n cancel out. So what are we left with now? Limit n tends to infinity 2 over n plus 1. Now remember, 2 is a constant. Plug the 2 out and take the n inside. What do we get? 2 limit n tends to infinity n plus 1 over n. Isn't this the same exactly as what we got earlier here? This one, guys, n plus 1 over n. Once again, what are we going to do? We're going to just pull the top terms apart, and we're going to get 2 limit n tend to infinity, n over n plus 1 over n, which is equal to, limit n tend to infinity, 1 over 1 plus n. And we all know what is 1 over 1 plus n, guys. This, as limit acts on it, this goes to 0. And we just simply have what? 2 times 1. The answer is 2. Okay, now we are going to go and apply the definition and relate these lower and the upper sums to the area of the region in the plane. So here's the definition. It says if my function is continuous and non-negative on a given interval, so here's line A to B, the area of the region which is bounded by the graph of the function, so this is the function, the x-axis, here's the x-axis, and the vertical lines x equals a and x equals b. Then the area is given by limit as n tend to infinity, summation, I varies from 1 to n f of ci delta x. Remember, these are what? These are the rectangles, guys. This is the ith rectangle we are having here, okay? Doesn't matter if you're having a circumscribed or an inscribed. In the end, when you take the limits, it actually is going to give us the same answer. So f of ci delta x, and this ci is a term in this rectangle between xi minus 1 and xi. Okay, and delta x is basically we're dividing this whole interval in equal parts, and we're making our lives easier. We say, hey, delta x is b minus a over n, because we're dividing this whole rectangle in interval in n with rectangles, n rectangles, and each rectangle has the same width. We're going to keep that thing handy. Every time we do a problem relating the area, which is using the limit process here, we are going to keep one thing in mind. We're going to have n rectangles, and that's n is the variable here. And then each of these rectangles will have equal width using this delta x. And c of I is in any value in the interval xi minus 1 and xi. So this is the ith rectangle, you can think of that. So this is the formula, guys, we will be working. So I'm going to do some examples here with you to show how do we apply and the limit process of finding the area of the region. Okay, so let's look at this one. Find the area of the region which is bounded by the graph of this function fx equals x cubed, the x-axis, and the vertical lines x equal to 0. Guys, remember this is x equals 0, and this line is x equals, this one is x equals 1. So we want to find the area of this function, and below this graph of this function fx equals x cubed, above the x-axis, between these two vertical lines. So if you guys remember, what is the formula? The formula, guys, is that we can only apply this one to find this area of the region. Very important that my function is continuous and non-negative in the interval we are looking at. So in the interval 0 to 1. Now remember, this is A and this is B. So if my function is continuous and non-negative in this interval, so what do we do? So this is how we apply this area limit process here for finding the area. So after that, what are we doing is we are going to partition this interval. So we are going to partition the interval 0 to 1 into n sub-intervals, into n sub-intervals of equal width. Keep that in mind. Equal width. What does that mean? I'm finding delta x, guys. Delta x is what? B minus a over n, which is 1 minus 0 over n. Just to keep in mind, I'm going to apply this formula so that you don't forget. I need to find the area. That means I need this. I am looking at this. So that means I need delta x and I need f of ci. I'm going to tell you how to find the ci too. And we're going to stick to that steps procedures. Okay. So the first thing is you say, oh, is my function continuous? Very good. It is continuous, non-negative in the interval we are looking at, 0 and 1. That's the one we're looking at, guys. That's the x-axis. Then we partition this into n equal subintervals of, so like this, we're doing that. And we're assuming that every rectangle we are having has the width delta x. Now we need to find out ci. Remember, that's what the formula is. Let me write that down if you forget. What's the area? Area is the limit n tends to infinity, summation I varies from 1 to n, f of ci delta x. So this ci is the one we're going to look at. This is ci, guys. Okay, this is ci. Hopefully I can make a nicer, okay, so let me try a nicer looking one if I can get it. FCI delta x. Okay, now how do we find ci? So we will always make sure that this is the formula I would like you guys to remember, that we're going to look at ci as the right endpoint. In other words, we're going to keep this in mind. A plus I delta x. So remember this formula. To find ci, we're going to write as A. A is the lower end of the interval. I delta x. So what is my A? A is 0. I remains I. I is a variable, guys. It's not the complex number. Please don't make that mistake. I is simple variable. Delta x we got from top, 1 over n. So what is ci? Ci is I over n. Now we have to find f of ci. Remember, formula is f of ci. Okay, what is f of ci? What's my function? F of x is x cubed. So ci, it is simply ci cubed. Do you see that over here? So what is my ci? It's I over n. It's I over n cubed, which is what? It's I cubed over n. So we have basically found out all the values of this variable, and we're just now going to plug and do the math. So what I'm going to do is I'm going to get a nice little more space for me to work on, and we're going to just plug and chuck the values out. So here's the formula. Area is limit n tend to infinity, summation I 1 to n, f of ci delta x. Okay, so limit n tend to infinity. Now summation remains the same. I 1 to n. Now f of ci is what? I cube. I forgot that. This is n cube, guys. Over n cube. And delta x is what? 1 over n. Now remember, the I is only on this part. Everything else is a constant for the summation. So we're going to take that out. Limit n tend to infinity 1 over n to the 4. And summation I cube, I varies from 1 to n. Now remember the summation formulas. That's why I had the rules out over there for you guys. Limit n tend to infinity 1 over n to the 4. What's the formula here? Remember, it's n squared because it's the sum of the first cubic terms. N plus 1 the whole square over 4. Okay, now do some little algebra. The square cancels out with this and we get an n square. What are we here? Limit n tends to infinity n plus 1 the whole square over 4n square. Now remember, now the limit is being applied on the n. The 4 is a constant. We can pull that out. So 1, 4, limit n tend to infinity n plus 1 the whole square over n square. Notice Both of them have the square, so we can put this expression under one, parenthesis. Your exponential rows, guys, I'm talking about, n plus 1 over n squared. Now remember, this is a familiar thing we have been looking at. So it's going to be what? 1/4 limit n tend to infinity. I can write this as 1 over 1n squared. Now we know how to apply the squaring formula here. Limit n tend to infinity. Oh, I forgot to write my 1 over 4, guys. 1 over 4, what do we get? 1 plus 1 over n squared plus 2 over n. Notice, when I apply the limit, what happens? The last two terms go to 0. So what is the final answer then? It is simply 1/4, and the limit of 1, 1, 1, 1 is simply a 1, is 1/4. Okay, and that's exactly what was given to us as the answer. It says the area under this curve for x cubed from 0 to 1 is 1/4. Here it is, guys. You see this one answer? And that's exactly what we got. One more example. We're going to apply the same thing, the same process we are going to follow, guys. Okay, in this one, guys, we are asked to find the area of the function between the interval 2 and 5. And then we're also asked to sketch the curve. So let's sketch and see what it is. 3x minus 2, it's a line. Okay, let's look at this. It's a line which is passing through on the y-axis minus 2. Just draw a line, minus 2. We're looking from 2. What's the value when the function is 2? It's 6 minus 2 of 4. Okay, so I'm assuming this is 4. And 5, because x is 2, sorry, when x is 2, the functions assume is 4. And then when x is 5, okay, guys, it's not a nice little, oh, God, okay, guys. Okay, so your 5 is here. And what's the value of the function when it is 5? So it's what, 15 minus 2, 13. Okay, so this is sketching the region. So I'm saying, assuming this is 13, somewhere up on the top is 13. And we say, okay, this is the region we want to find. Now we're going to apply the limit process. Okay, remember, this function is continuous. It is non-negative in the region 2 to 5. So we can apply that theorem. And so what you're going to look at, very important, keep these things in mind. Area, limit, n tend to infinity, summation f of ci, delta x, I varies from 1 to n. Okay, so the things we need to know. What's my delta x? What's my ci? What's my f of ci? Very, very important. Okay, guys, so let's start it. Here's it. What's my delta x? My delta x, now remember this is my a and b. It's b minus a over n. 5 minus 2 over n. 3 over n. Okay, we got my delta x. Remember what's the formula for c of I? We're going to stick with the ones we learned. It's a plus I delta x. What's my a? 2. It's 2 plus I delta x is 3 over n. So what is of c of I? It's 2 plus 3i over n. And then the last thing, because you're looking for f of ci. F ci. What's this? This is my function f of x, guys, keep in mind. So it's 3 times ci minus 2. Plug in the value for ci, it's 3 times 2 plus 3i over n minus 2. Let's just do a little algebra here. We are getting 6 plus 9i over n minus 2, or we are having 4 plus 9i over n. Do you see that here? Okay, so we got a f of ci. Now we have to apply and plug in the values. So once again, I'm going to increase my space and do all the work we did. Okay. So we start here. Area is the limit n tends to infinity, f of ci, delta, oh, exactly, forgot these summations, guys. Be very, very careful. Okay. Summation I varies from 1 to n, f of ci, delta x. Now let's plug in. Limit n tend to infinity, summation I varies from 1 to n. F of ci was what? Remember here? It's 4 plus 9i over n, guys. Here's my f of ci. Okay. So, which is 4 plus 9i over n. What was my delta x? Let's look at delta x, guys. That's my delta x, 3 over n. A suggestion, guys, when you are trying to do these problems, first try to make your algebra to the easiest form you can. So I will actually distribute my 3 of n before I do the summation rules. So this is what? Limit n tends to infinity, summation I varies from 1 to n. So it's going to be what? 12 over n plus 27i over n squared. Now note, 12 over n, guys, is like a constant, and we're going to apply the summation rules. So limit is simply outside, and summation, we're going to have I varies from 1 to n, 12 over n, plus, now this is what we're going to do, summation I varies from 1 to n, 27 over n squared I. Now 27 over n squared, guys, is a constant. 12 over n is a constant done n times. So what does that mean? Again, you go to the rules of the summation, guys. Please make sure you have your rules handy. Okay, so this one, the first one is basically 12 over n times n. Okay, plus. Now this is 27 over n squared out, and sum of I varies from 1 to n. This is n, guys, okay? So this n and n cancel. What do I have? Limit n tends to infinity of 12 plus 27 over n squared. Now some of the first n terms, this is basically n into n plus 1 over 2. You know, familiar terms we've been looking at, guys, many times now. This n and this n cancel out. Now it's simple algebra, and then you apply the limits we learned in chapter 1. So this is going to be 12. Now 27 over 2 we can take out, guys, and this n can go inside, n plus 1 over n. And notice, what is this going to become? Limit n tend to infinity. I'll have to open up more, which is going to be 12 plus 27 over 2, 1 plus 1 over n. So what happens now, guys? Now remember, this is the big one. So as now limit can be applied inside. This is going to be simple 12. This goes go to 0. So what are we going to get? 12 plus 27 over 2. And what do we get? The answer to be 51 over 2. So this is what? 24 plus 27? 51 over 2. Guys, very important when you're doing these problems. Let me say something, you know, in terms of how when you're doing these problems. So when you're doing this one, guys, I want you to keep in mind the delta x, the ci, and the fci. If you keep these formulas handy, you will not make mistakes. Make sure that you do these first, okay? Once you have done them, then go ahead and plug the values in the formula. Now, when you're plugging the values in the formula, go ahead and solve as much as you can before you do the summations and the limit. So once you have got this one, then you have to remember the summation rules. And once you get the summation rules, then you have to remember the limits, and specifically the limits to infinity. And then you just get your answer. Okay guys, we are done with the major concepts in section 4.2. So what my recommendation to you is, practice these 4 problems. Exactly go by what are the things I have done earlier with you. So when you practice these problems, will help you definitely later. Thank you.